Do a mic check here. I think we're okay. Good morning. Hopefully everyone's doing good this week. What are we on? Monday. So hopefully you had a good start to your week, let's say. Let's see. Good morning, Captain Price, Glazer, Ursavax, Neonat. Good morning to all of you. If I can't see in chat, good morning to you too. Hopefully everyone's feeling good about things right now. Did I have you guys do a pat on your back thing? I think I did. So anyway, it was nice. There were lots of nice comments in the pat ourselves on the back discussion. So thank you for that. That was pleasant to read. And hopefully it was sort of represented a small break for you. Hi, good morning. Morning Etsy is here too. So we're here. We're over the hump. We're over the halfway point. Your big thing left for this semester, I mean, I know we have the work every week, but the second individual project, I will point out to you where, but this week's lab actually has a thing that a couple of things that you want for the second individual project. So you may not be ready to get started on the second project, but you are starting to get some of the building blocks for it this week, so it's a good time to start sort of taking note, maybe actually literally taking note of the things that you can get from the upcoming labs and use on the second project. So just heads up about that. Okay, so week 9. This is kind of a fun thing, and I'll also try to point out to you where and how you can use these techniques in high-level programming. But we're doing bitwise logic, and it's a little weird because I know we did the stack last week, but you probably also have arithmetic on your mind, and bitwise logic is not arithmetic as we think of it. So try to remind yourself as we're doing this that we're not doing math. Bitwise logic is slightly different. But it's quite cool and it's quite powerful. You will use it in high-level programming. You may or may not use it to solve a problem, but hopefully you choose to use it to solve a problem someday. But you will see bitwise logic employed sometimes in libraries, and I'll try to show you an example of that as well. Okay, so week 9. I'll just step through as we always do. Alright, so the goal here is that you understand how the fundamental bitwise operations work. If you already know this stuff, then that's great, you're a little bit ahead of the game, but for a lot of us, you probably haven't ever directly used any of these things. So we have the bitwise AND operation, bitwise OR, bitwise exclusive OR, and bitwise NOT. I'm saying bitwise, and what I mean by that is that the easiest way to understand how these work is to view them as they work on binary numbers, bit by bit by bit on binary numbers. Yeah, so Glazer asked, are these like logic gates? And yes, they are. So on the hardware, there are actually logic gates that represent these operations. And then in assembly language programming, we have instructions that we can actually cause these to be executed. So good question. And yes, these are like logic gates. So if you've been exposed to logic gates, then you know what's coming. And then I'll show you where we're using, I don't remember if I actually ended up using rotates, but I'll show you how those work too. So you will see how we can use shift in programming today, which is another bitwise operation, but the important ones for you. Oh, are you guys doing logic gates in another class, I assume? So this is kind of coming together with another class's content, which is awesome. It's very, very cool. Okay, so we'll also talk a little bit about shift and rotate, and I'll show you at least an example of how I'm using shift in this week's lab code. I also have my overhead camera. Oh, discrete math does it. Okay, yeah, I guess they would, wouldn't they? Yeah, so some of you have seen it in discrete math, or if you've taken circuits, if you're one of the engineers, then you may have seen it in that context as well. Awesome. I quite like the bitwise stuff. The first time I realized I could use bitwise operations to solve a problem, I was pretty excited about it. I felt so computer sciencey that I was using it to solve a real problem. It felt pretty cool. Okay, just one section of the text, logical operations on bits. I'm going to go back one step and just sort of point out to you that there are x86 instructions. I think I said that, but anyway, we'll look at how these operations work conceptually with me drawing pictures, and then we'll look at how they work as instructions inside of a program. So we just have the one section where we're focusing specifically on the bitwise or logical operations is what they call them, but it's not logic in terms of greater than, less than. It's logic in terms of how we describe the circuits that execute it. Homework is always from that reading, the lab, which I'm going to come back to here in a second. The discussion, so the discussion this week will challenge you to figure out how people use bitwise operations in the real world. They are used in the real world in programming. So the challenge for the discussion is to see if you can find some examples of how these bitwise operations are used. And then the reminders, so just the regular stuff. The individual project, it's not due until the 16th, the end of the 16th week of the semester, but it is out there, and now is the time. I'm just sort of calling your attention to it. Now is the time to start pulling things out of the weekly labs that you can use. So either start doing the code for the project if you're comfortable with that, or at the very least do something to make note of the lab and what from it is very, very useful for the project. Okay. Now I'm going to sort of step off and do an aside. It's not super an aside, but a little bit of an aside, and then come back to the lab. So I had a request by Canvas Inbox to talk a little bit about the graphing function from last week's lab. So I'm going to do that before I do any of this week's stuff. So anyway, quick aside. I won't go too quick, but anyway, we're going to go just revisit the graphing thing from last week. And we also have a loop that looks like this week, so it can be helpful. So let's get my virtual machine. Okay, so quick aside, let's talk about the graphing function from last week. And I'm just going to break it down in detail to make sure that everyone understands it. And again, this is by request that we talk about the graphing function, and in particular the loop inside of it and what's going on there. So it's a good question, and let's go explore it for a few minutes. Okay. All right, so the graphing function from last week. And I'm not going to write a procedure for this, for the example. I'm just going to do the algorithm and talk about how it works. Make sure I get this in the right place. HLA somewhere. Okay, that looks decent enough. I'm just making sure I have the chat where I can see it. Okay, so let me just show you the problem that we're trying to solve. So Actually, let me do it as a procedure so you can kind of see the problem we're trying to solve. Okay, so what we're trying to do is take a number and kind of like show a bar graph form of it. So we have code that spits out the number, and then a little arrow just because I think it looks attractive, and then we have a loop. We're going to use the C register as a counter here, and you can use ECX here, or CX, or CL, or even CH if you want to. The choice of which register depends on how many times you need the loop to execute. So the reason why I can use CL here is because initially I'm going to loop it as many times as the number is, and since the number is an UNS8, it's safe to use an 8-bit register because I know that this will never exceed the bounds of an UNS8. So it's safe to use CL. I could have used CX if I wanted to, but CL matches the size, so they are comparable. So that's why the choice is CL. Anyway, CL is I hope I have that do right. It feels wrong, but it's right. Okay, so this is int I equals 0. The CL is the I. Int I equals 0. I less than however many times you want the loop to execute, and then I plus plus. So that's the setup part of the for loop. So this is the for loop as HLA can handle it because it doesn't have the assignment operator and it also doesn't have the plus plus operator in it. But it can do comparisons. It does have access to the x86 increment instruction, and it does have access to the x86 move instruction. So int I equals 0, I less than the number itself, I plus plus. And then what we'll do is, as a means of putting out a bar graph, we could put stars, we could put pluses, we could put @ signs, or the pound sign, or the dollar sign, or whatever we want. I think I'll use pluses because that's what I want to use. So for whatever value of the number there is, we're going to put pluses. So if the number is 10, then the little bar graph will be 10 pluses. If it's 20, the little bar graph will be 20 pluses. And then I can do a show graph, and I'll just give it a bunch of numbers that would fit in UNS8, like a 20, a 99. I'll just do 3 of them, and then like a 3. Okay, so I'm going to show the graph 3 times on the value 20, which should be 20 arrow 20 pluses. Show graph 99, which should be 99 arrow 99 pluses, 3 arrow 3 pluses. What do I call a graph? Oops, I forgot new lines. So after I get done printing the bar, I should put out a new line. Okay, so that's kind of where we start with this bar graph idea. Now, what I would immediately notice myself if I were testing is 99 looks terrible. So usually these terminals, the tradition is that they are 20 rows tall and 80 columns wide. So you usually end up writing code that tries to respect the fact that most people by default are probably only going to have 80 characters of width on their terminal. Now I could stretch this out, it's true. And then rerun it and possibly get close. So there, all 99 fit. But on most of these kinds of systems, they're going to be 20 and 99. In fact, I'm going to close that and I'm going to reopen it to the default. So I just want you to notice that by default, you typically get 20 rows high and 80 columns wide. Okay, so yeah, so now the question becomes, well, if I don't want 99 to spill over the screen and make a huge mess, then I need to section that off somehow. I need to, instead of printing one for every like 99 pluses, maybe I should just print 1 plus for every 10 in the value of 99. So good one, Glazer. So it's a good question by Garcivox. How can we print it 1 for each 10? And the answer is to divide it by 10. So we can print out the number. That's perfectly safe. But now what we really need to do is, instead of printing 99, let's just print 1 plus for every 10 of value, which is where divide comes in. So we're going to move the number into AL. We're about to do a division, so we load up a numerator in AL. I know that I'm doing 8-bit division because number is an uns 8. I zero extend. And remember, that's going to receive the remainder, although I don't care about that in this case. And then I'm going to fire off the divide. So I'm going to divide that by 10. So I'm going to end up basically dividing the number by 10, and then AL will contain the quotient. AH will contain the remainder. I don't care about that. So I've done the division. I end up with AH has the remainder, AL has the quotient, and it's the quotient that I want. So now in my loop, instead of looping for every one of the value, I only loop for every 10 of the value that I computed by division. So now 20 should print out 2, 99 should print out 9, and 3 should print out none because it never reaches 10, right? So if it's less than 10, you don't even get 1. And that was the whole point of that show graph thing on last week's lab, is usually on a terminal, in a terminal environment, you should assume that you only have at most 80 characters to work with. And that's somewhat arbitrary, but it's sort of the traditional default is 20 high and 80 wide. So usually when we do console output, we write code to account for that. You're welcome. So there's a walkthrough of that algorithm. But it was useful because I'm positive that other people really needed a good breakdown of how that, why that procedure is there and what it is that it's doing. Okay, so there's our aside. Now let's go back to bitwise stuff. Let me change my display back. Okay, so bitwise stuff. In fact, we don't need that. We want my camera. So I know you love the camera. It's a little bit old school. I do have a tablet, but I spend more time fighting the tablet than drawing pictures, so I just gave up on the whole idea and I'm just using paper. I'm just much more comfortable with the paper. Okay, so bitwise logic, what does that mean? What that means is it takes 2 strings of bits. I'm just going to make some up. I'll use the percent sign like we do in HLA. Takes 2 string of bits. So when we say bitwise, we mean that the operation is not like arithmetic where you have carries and stuff. Bitwise means just bit by bit by bit by bit by bit. And whatever happens in one column of bits when you apply a bitwise operation does not affect the other column. So it takes a little bit of getting used to in the brain. But bit by bit by bit, that's what we mean by bitwise. It just is going to apply to these partners of bits, and whatever happens to these 2 partners of bits doesn't affect these 2 partners of bits, or these, or these. Hopefully that makes a little bit of sense. So let's do bitwise and first. So I would write it like this as a problem. So what does it mean to say this string of bits and this bitwise operation, this string of bits. So the rule for AND looks like this as a logic table. So if both bits are 0, the result is a 0. This is the same, by the way. Logically, it's the same as using the double ampersands in like C++. So if you think of zeros as being false, then a false and a false is false. So a false and a true is false. A false and a true is false. A true and a true is true. But I usually don't think of it as the false true stuff, but if it helps, think of it that way. I just think if you have two zeros, you get a 0. If you have a 0 and a 1, you get a 0. If you have a 1 and a 1, you get a 1. So now let's apply it to these two strings of bits. So remember, there's no carries or anything. It's just this pair. Then ooh, look at it. It focused for a second, which I thought it looked a little crisper for just a second. Okay, so a 0 and a 0 is just 0. A 1 and a 1 is 1. A 1 and a 0 is 0. A 0 and a 1 is 1. A 1 and a 0, 0. A 1 and a 1 is 1. 0 and 1 is 0. 1 and 0 is 0. So, if I apply, that's correct, Captain Price. So the AND gate is only true when both of the input bits are true. I don't know why I wrote. That may be what you were responding to. For some reason I wrote a 1 there. So the result of ANDing this value with this value is this value. It's not math. It's just the result of applying that bitwise operation to the bits with these two values side by side. So I end up with 0010, 0010. It doesn't really mean anything in terms of a value. All it means is this is the bits that came out by applying this operation. Now there are applications for it, which I'll try to describe for you, but that's how bitwise AND works. For now, I'll just worry about if I have these bits and these bits. So let's try one with decimal numbers, just to make it interesting. So what would it look like to have 9 and 4? That's true. So Captain Price is pointing out in discrete math you have visuals where you look at the logic gates, but here in assembly we're actually sort of imagining how the processor is actually sort of jamming the bits through the circuit. And then ultimately how can we use that to generate useful information. Okay, so if I say 9 and 4, that's meaningless. You do. So you would convert these to binary, which is what we're going to do. So the point here, though, is that you can do 9 and 4, but you have to be ready for what that means, because it doesn't mean math. It really just means passing the bits that are 9 through the bits that are 4 with the AND operation and seeing what the result is. So let's turn it into binary. The upper nibbles on both are zeros. A 9 is an 8 and a 1, and a 4 is simply a 4. So you can do 9 and 4 because it's just a representation, right? So you can represent 9 as bits and 4 as bits. You just have to remind yourself that this is not arithmetic. This is passing these bits through these bits and applying a particular bitwise operation to them. So if I pass these bits through these bits with AND, I end up with 0, as it turns out. Because nowhere are both bits going to line up and produce an AND by the rules of, or produce a 1 by the rules of the AND operation. Yeah, that'd be nice, Captain Price. If you've made a table already, that'd be awesome to share that. You can actually add that to this week's discussion as your contribution, is to show people the gates. Okay, so passing those bits through those bits, applying that operation yields a 0. So there is one interesting thing. I'm going to change this to a 5, and then I'm going to update this. So if I change the second bit, so I'm passing the bits that are 9 through the bits that are 5 with this operation. So I updated the binary, so that's a 4 and a 1. I end up with this result, which in decimal looks like 1, although that's largely meaningless. But one thing that it does tell me, and this is sort of to think about, wherever I get a 1, I know that that was the location where both of those values had the bit turned on, had the bit set at 1. So if I'm using this kind of like a filter, I can use AND. I can pass these bits through these bits, and the result will tell me where both of those values had their bits set to 1, which can be useful. Okay, so there's AND. So a lot of you already know this, but if you don't, we'll just do it. So let's do some ORs. Let's make that a 1. Okay, so bitwise OR. So you guys who have had discrete, you know this. If we do this as a truth table, this is similar, but again, I find it useful to separate them in my head, that when I'm doing bitwise logic, it does kind of have the same results as sort of what we think of as regular logic, if statements and whatnot. Oh, that's cool. Yeah, so Captain Price, if you have tables that show all those goodies like Venn diagrams and symbols and gates, that'd be excellent to share that. Okay, so bitwise OR. It does kind of function similarly though. So if you think of 0 being false and 1 being true, well, false or false is still false. Or 2 zeros is a 0. False or true is true. False or true is true. And of course, true or true is also true. So, yeah, so OR gates, bitwise OR, you get true if either one of them, if either one or the other is 1, then you get a 1. So very, very different, right, from AND. Bitwise OR, you get a lot more 1s out of it. So let's apply OR to these bit strings and see what happens. So 1 or 1 is simply a 1. 0 or 1 is a 1. 0 or 1 is a 1. 0 or 0 is a 0. And notice there's no carries or anything. It's just pair by pair by pair, bitwise, bitwise, bitwise. 0 or 1 is a 1. 1 or 0 is a 1. 0 or 0 is a 0. 1 or 1 is 1. So I end up with this bit sequence. That's not an H, that's meant to be a percent sign. It is not math, remember. It is just the result of applying a bitwise logical operation to these two series of bits. Typically, by the way, you end up with a lot more, of course. Okay, so I'm going to do one that's going to look silly at first. But then we'll update it. Just to sort of think about what OR can do. So if we take the value 8 and we OR it with 0, well, the first thing to do to know that you're getting it right is to write down in binary. So there's binary 8, and then binary 0, of course, is all zeros. So if we bitwise OR these together, we actually end up with the same value that we started with. So we get zeros everywhere except for this place. But now let's see what happens if we change this, let's say to 3. So if I pass these bits that are 8 through the bits that are 3 using the OR operation, that would be this. The result is that I actually turn on or flick to 1, or however you want to describe it for yourself. I turn these two positions into 1s, and I don't lose the original 1. And this is a thing, again, to keep in your head. One use of OR is to target certain bits in a sequence to be turned on. If you OR something, let's say that we turned it into 11. So OR does not change what you started. It doesn't turn anything off, in other words, but it can turn things on. So OR is an interesting and useful technique for switching on specific bits in a pattern that you want to switch on to convert into 1s. Okay, so that's OR. How am I doing on time? I'm doing okay. Logical OR, let's do exclusive OR. I'm just making up, these I'm just totally making them up. Okay, so exclusive OR. Exclusive OR's truth table. Basically, the way to remember this is exclusive OR gives you a 1 when the bits are different. So 0 and 0 exclusive OR 0 gives you a 0 because they're not different. 1 exclusive OR 1 gives you a 0 because they're not different. They're not exclusive of each other. So a 1 and a 0 will give you a 1 because they are exclusive of each other. And a 0 and a 1 will give you a 1 because they are exclusive, meaning that they're different from each other. So that's the whole rule. If the bits are different, you get a 1. If they're the same, you get a 0. So here's 0 and 1, so they're different. These are different. These are different. What am I saying? These are not different. These are not different. These not different. These are not different. These are different. And these are different. So if I pass these bits through these bits with exclusive OR, this is the result that I get. It's pretty. That's just an accident that I got a nice pattern out of it. That's exclusive OR. And then I'll show you, again, just to remind you that you can apply these to integers. You just have to remind yourself that it's not actually doing math, it's doing bitwise logic. So if I say 9 exclusive OR 8. Let's just see what happens. The 9, well, both of them, the upper nibble's blank. 9 is that, 8 is this. I end up with this bit pattern. My hand's getting tired. I end up with this bit pattern. Doesn't really mean anything, it's just the result of applying, taking this string of bits through this string of bits with the exclusive OR operation. This is the result that I get. Here's one interesting thing about exclusive OR though. If I change this to 9, I end up with 0. So it doesn't seem all that useful because can't I just use a move operation? But one thing you can do with exclusive OR is you can actually get 0 by exclusing OR something with itself. So if you exclusive OR something with itself, you get 0, which is just a thing. I don't know how many of you have taken P&A 2, but something that's interesting, if you're interested in such things, if you Google XOR, exclusive OR, and linked list, you'll find that there is an algorithm out there that generates the links in the linked list using exclusive OR. It's kind of cool. You probably won't do it in school, but it's an interesting application of exclusive OR in an algorithm that creates a linked list. Now, if you haven't taken P&A 2, then you probably don't know linked lists. But anyway, you might just note this down. It would be useful for someone to throw into the discussion to go look at that algorithm. It's a neat application of exclusive OR. Okay, the last one, time. Okay, we're doing good on time. The last one is not. And it does basically logically mean what you think. If you've used not in a high-level language. Okay, so one thing about not. It does not, you don't apply it by passing one string of bits through another string of bits. You just apply it to a string of bits. And all it does is reverse the bits. So the truth table is a very simple one. There's only one input at a time with not. So not just means the opposite. So if it's false or 0, it's 1. If it's true or 1, it becomes 0. That's it. So not just flips the bits around. To be the exact opposite settings of what it started out as. So not only uses a single operand. It does not take two operands and mush them together bitwise. It just takes the bits of one operand and reverses them. So if you did, oh look, this is my last piece of paper on this pad. So you might do like not 11, let's say. There, it caught up with me. Not 11. So you convert the 11 to binary. So I need an 8 and I need 3 more. So not 11 looks like this. It's just literally the opposite bit settings of what you started out as. Again, it's not math. If you look at it as decimal numbers, you can turn it into decimal numbers, but it doesn't mean a whole lot as decimal numbers. Okay, that's the bitwise logic operations and truth tables. And you have a classmate, Captain Price, has offered, and that would be a really cool contribution to show some sort of extended from discrete math truth tables. And if you have materials from discrete math, throw them in there. It'd be terrific. Okay, so it's already there on Piazza, which is awesome. Anyway, okay, so there's not. So and, or, X, or, not. They have applications, like why do I even care about this and? There is a use for them, which is sort of the second layer of this is, okay, how do they work? And then the second layer would be, now what could I use them for? Hopefully I'm going to have time to show you that here as I get the lab kind of spun up a little bit as well. But I'll just tell you, I'll give you some hints real quick. So, and, where I have used and where I see people using and, you can use it to check a bit string to see which bits are turned on. So if you're clever, you can use and to detect the settings of a bit string, like which ones have ones on them. So this is for detection. Or is for setting. So you can use or to enable or change to one target bits. XOR, there is a clever algorithm for linked lists, and you can also use it to zero out. I haven't used this anywhere else myself, but I'm sure there's other applications to it. Not, you're going to see, because there's an algorithm to convert a positive number in binary to a negative number in binary by using the not operation on it. Okay, so, but that is sort of the second level of stuff is, how do they work is the first level. The second level is when and why would I ever use these things. So I'll try to give you a demonstration of that. Probably after I get the lab spun up a little bit. Okay, I think I can get rid of the pad, which didn't seem to get rid of, did it? Oh wait, the camera is what I want to go away. Camera go, browser go, okay. So there's the bitwise operations. Oh, I might need the pad back. Well, if I need the pad back, I'll just bring the pad back. Actually, Firefox first. So let me go grab the lab and let's do a little bit of setup on it. I'm still doing okay on time. Get the raw stuff. And then I'll also kind of tell you what's going on in the lab. And this is the time. No. Desktop. Lab 9. Okay. I almost messed up myself and lost all my notes. Okay. So let's look at Lab 9 and see what's going on in here, and then I'll explain to you the sort of weird stuff. So one thing is, we have a new version of getNumber. It's fully implemented, but this getNumber procedure, you want it. Or you're going to need a variant of it for the second project. Now you're going to see variants of it in the next several weeks. What it does differently is this try exception and try stuff. Experiment with it. But the point of this try and try stuff is, you've probably experienced this. If you need to do an unassigned 8-bit integer and you put a negative number, at present for most of you your software will crash because a negative number can't be an unsigned 8-bit integer and the program just crashes. Or let's say that you prompt them for an 8-bit integer and they type in their name. Oh, you can't see the machine? You can't. That's true. Sorry. Okay, so I'll go back a step so you can see the see what I'm talking about here. So this is, I've been talking about this getNumber procedure. Now it's not checking for min and max right now, which could easily be added. What it is doing though is it is now instead of crashing when the user types in something that's illegal for an unsigned 8-bit integer, it will detect that problem and give them a chance to type a new one. So the whole trick is this try, any exception, and try. So in HLA, when you do a get U8, if you type a negative number, the program will crash. But technically what happens is it throws an exception, is what we say. Or if you type a name when it was supposed to be a get U8, the program will throw an exception and then the program will halt. So, hopefully you can see the machine now. Yeah, okay. And in the absence of the try, any exception, and try stuff, an exception, something that causes an exception, a negative number or a string or something, the program will just halt. Now that we have wrapped it in this try and try stuff, the program won't halt anymore. The program will actually give us a chance to get more input. So that's what this is all about, is if they enter something that's illegal for an unsigned 8-bit integer, the program no longer crashes. It prints a warning, like whatever you typed in is not an 8-bit integer, and then it keeps them in the for loop until they give a valid input. This part is a little bit confusing, and the way exceptions work is a little bit confusing, so I'll just try to describe it here, and if we have time we'll spin up a more detailed example. So when you enter a try, we call it a try block. When you enter a try block, what you're telling the system is, I'm about to do something that could cause an exception. And an exception is basically a bad error. And one type of bad error is I need an unsigned 8-bit integer and they just typed in their name, or they just typed in a negative number, or they typed in a number that's way too big. So what happens on this get U8, if they type in something naughty, it throws an exception and the flow of the program immediately drops down into this exception block. So if there is an exception section, instead of halting, the program will actually do whatever the exception section says to do, which in this case is simply print out a warning. So since we are now detecting the exception on a bad input, the program will no longer halt. It will actually print out an error message, and then the for loop will keep executing. Now, if they type in something that's illegal for an unsigned 8-bit integer, the program will continue flowing to the next line down. So instead of jumping from here to this exception section, the program will just flow to this unprotected section. Now, unprotected is just an unusual HLA thing. You need it there. If you don't put it there, eventually errors will crop up in weird looking errors. So I think we could spend time talking about that. I think it's just safer to say right now, in HLA, you need this unprotected thing to sort of clean up when everything has gone well. So if we hit unprotected, that means this was successful. So we just do the flush input thing and then we break out of the loop. That's it. So the long and the short of it is, this get number procedure can't be broken by bad users anymore. They have to type in an unsigned 8-bit integer, and until they do, the program will be stuck in a loop. So that's an improvement. It's not doing a range check to see if they are within a certain minimum and maximum, but that can be added. And we will add it in coming weeks. So this is one to make note of. You're going to want this as a building block for the second project. This next one down is also a building block for the second project. So you're going to want this for the second project. It's complete. It already works as written. The reason why you want it, it will require a little bit of alteration for the second project. But the reason that you want it is because on the second project you're going to have to print out some values in binary. HLA does not do binary display on its own, so you have to do some work to make that happen. Now I'm going to explain this one in detail here in just a second. Yeah, I'm doing okay on time. But this is one to make note of. This is another function in Lab 9 that will be very, very useful in the second project. It does a little bit of calculation trickery, basically to convert an unsigned 8-bit value into what looks like binary output. It's a neat little trick. It's the same trick, by the way, you would use in C++ if you wanted to do this. So there's print binary. Go again. I assume at this point you're tired of copying and pasting that in, so I just provided it at this point. And I think that we've all practiced it enough now that I don't need to hide it from you anymore. Hopefully, though, you sort of have developed a little bit of confidence about your ability to move code around. Okay, so go again is useful, but you've already got that in a whole bunch of different places. And then we have the main part of the loop itself, which for most of you can probably figure out without my help, but I might do a setup on one of these. So I've already done bitwise AND. And what I've done is, so for this section, I copy their first input, so they have two inputs, a first number and a second number. So I copy one of them into AL, and then I use the AND instruction to pass them through each other, the binary of them, to pass them through each other to see what the result will be. Then I use the print binary function to print out the first number in binary, and then the string AND, so that my user looking at the screen knows, okay, AND is being applied here. And then I use print binary to print the second number, and then a little equal sign, and then the result. So this AND is the same thing as AL equals AL and number 2. And since we already loaded up AL with number 1, it's the same thing as AL number 1 being bitwise ANDed with number 2. Remember, this is not math. It's just looking at the result in binary of what happens when I pass one set of bits through another set of bits. You might experiment with reversing the order of these things. You'll find that the order doesn't matter. I can do number 2 and number 1, and I get the same exact result. Okay, so that's the AND section. Checking the time. Let's do the, well, I'll explain them. So we're going to do one with OR. Then we're going to do XOR. Those are both going to be set up in the same way as AND. And then notice that there's a bitwise not for number 1, and the reason why they're separate, bitwise not for number 2. The reason why they're separate is because you don't not two things together, you just take one value and you apply not to it. Maybe I'll do one of the nots. Okay, bitwise not. So the first thing to do is to copy number 1 over into a register. It doesn't really matter what register as long as the size matches. But as long as the A register is available, which it is, I'm going to use it. Now, the reason why I'm copying number 1 into AL is because I don't want to do anything that might destroy number 1. I want to keep it around, just in case it's needed later. So I copy number 1 into AL, and then I not AL, because these are one operand instructions. And then I will say print number 1 in binary. And then I will output, in fact, I should do the not first, shouldn't I? I should say not. I did not put a new line here, by the way, because I want not space number 1 space equals space. I want everything kind of mushed together, so on one line. So I'm not putting new lines on purpose. And then at the very end of that, I'll go ahead and put out a new line. So print the number in binary, and then I'll print the knotted value in binary to see the result. I'm going to go ahead and build that and see what it does. Hopefully it compiles. Okay, thank goodness it does. All right, so here's the numbers. I'm just going to pick like 10 and, oops, my nums lock is off. 10 and let's say 21. So here's the 10 from the print binary function, which looks right. It's an 8 and a 2. And the 21, so that is 16 and 4 and 1. Those ANDed together yielded zeros. And I'm going to check that real quick. Yeah, that's correct, right? And then if I not my 10, that's my first number, then I get the exact opposite. So that's all correct. Alright, so now I want to go look at, I have to bring up my camera again and draw pictures of this, but I want to just explain to you how print binary actually works. Because it looks a lot scarier than it actually is. And in fact, I'm going to make a new program just to show that. But let me show you the trick. The whole trick really is right here. This SHL and then this if at carry. So let me show you how SHL works. And chat, if you notice me mess up my display, please let me know. Because I mean to have the tablet, and I think I have to go on the back page because I ran out of note paper. Okay, so let's talk about logical shift left. So SHL instruction, logical shift left, which in x86 assembly is SHL. Oh, I don't need to show you that yet. Okay. So let me just make sure I still got my display. So the way you use it is you shift an amount and then the value you want to shift. So that's what it's going to look like when we call it. We're going to shift left by a certain amount to shift and a value. Now let me show you how shift left works. If I take a value like this, and let's just do shift left by 1. Let's say that this is in AL. So if I shift left AL by 1, what does that mean? So what happens when you do a shift left is every bit in here is shifted to the left the number of positions that you specify. Now I'm specifying 1 position. So every bit in here is going to shift over to the left by 1. Now what's going to happen is this bit here, when it shifts left 1, it falls off basically. But on x86, when a bit falls off from a shift, it actually goes into carry. So when you do a shift left by 1, you can actually tell if anything fell off by checking the carry bit. So if I shift this value left by 1, this 1 right here falls off and goes into carry. And then all these bits shift over by 1. So I'm going to end up with a 0 because that bit shifted over. This bit's going to shift over 0. This bit's going to shift over 0. This bit's going to shift over 1. This bit's going to shift over 0. This bit's going to shift over 0. This bit's going to shift over 1. And then what x86 does for a shift is it fills in with zeros. So if you shift left this value once, you end up with this value plus a 1 that fell off into carry. You can shift left by as many as you want, but it's only when you shift left by 1 that you can detect if something fell off into carry. Now it turns out that in this case that's what we want. We're going to shift left by 1, and then we're going to check the carry bit to see if anything fell off. So let's just look at an example value and see what would happen if we shifted it left a whole bunch of times. So I'm going to keep track of my at carry bits. Yes, you can shift right, Glazer. So Glazer is asking, can you shift right? And yes, you can. It works exactly the same way, except for everything goes to the right. So if you shift right by 1, the furthest right bit, it falls off and goes into carry. You can shift by more than 1. It's just that it's only when you shift by 1 that you can actually tell what fell off. If you're clever, by the way, you might realize that shifting left has an effect on values. Like if you shift left 1, you end up with 2. And if you shift left 2, you end up with 4. And it works the same way in the other direction. So 1 becomes 2, 2 becomes 4, 4 becomes 8, 8 becomes 16. It is a way in some cases that you can divide, or in this case multiply by shifting left by 2, or divide by shifting right by 2. It depends on the value sometimes. So kind of neat. Okay, so let's see what happens if we take some arbitrary 8-bit value and we shift it left once, but 8 times. And the way we'd achieve 8 times is in a loop. So if we put this in a loop and repeated shift left 8 times, what would happen? Well, on the first shift left, this 1 right here would fall off. On the second shift left, this 0 would fall off. On the third shift left, this 0 would fall off. On the fourth shift left, this 1 would fall off. The fifth, this 1 would fall off. The sixth, this 0 would fall off. The seventh, this 1 would fall off. And the eighth, this 0 would fall off. By the way, if I did this, if I repeated the process of shifting this left 1 bit at a time, 1 position, 8 different times, what would the result be? Like, what would I end up with here? Let me block that. Zeros. That's right. Good one, Tyler. So you'd end up with all zeros. So that's something to be careful of because shifting is destructive. If you shift a value, you end up with 0 ultimately. It destroys the value. Before I go talk about the algorithm real quick, I'll point out to you that you can also rotate. I decided not to use them in the lab, but there are instructions to rotate. And what rotate does is instead of shifting them and they fall off, it rotates them back around to the front. So you can rotate values, and it takes, if you're rotating right, so if I take a value like this, and I rotate it right by 1, then this bit actually rotates around to take the place of this bit, and all the others move over to the right by 1. So if you were to rotate 8 times, you'd end up with the same value you started out with. You can also rotate left. Is another operation, but we don't have any good use for it, so I didn't include it. But you can also do rotates. Okay, so now let's go back and look at that algorithm real quick. And okay, I've run over, but hopefully not too much over. Dock camera off. Okay, so let's at least look at how this algorithm works. And then if anyone wants, you can ask and I'll break it down. So we have a value and we want to see it in binary, and HLA won't do that. So we're going to use the shift trick. So we're going to put out a percent sign. That's just because in HLA it's nice to show percent because that's how they're represented. And then I copy the value into AL. Here's the doing the thing 8 times. The reason why I need to do this 8 times is because I know that the value is 8 bits long. So if I'm to see all of the bits in all of their glory, I'm going to have to do a process 8 times on the individual bits. So I have the value in AL, and what I do each time is I shift that value over once to the left. And what happens is the leftmost bit falls off. Then I immediately check carry to see if it's got something in it. If it does, I know that a 1 just fell off, so I print 1. If it doesn't have anything in it, that basically means it's got a 0 in it, then I print a 0. After I've done the 0, 1, 2, and 3 passes, that's the first 4 bits, I put an underscore out there just to make it look prettier, and that's it. So the whole trick here is I use this shift left once, check the carry bit, and either print out a 1 if something fell off, or a 0 if nothing fell off, a 0 fell off. And then I put, after the first 4, 0, 1, 2, 3, I put an underscore out to make the binary look pretty. So that's the whole trick. I also use push and pop to protect and preserve the registers, right? So I'm using the A register for my shifty one and my C register for the count. So I push those and then I pop them in the reverse order. So that's the whole trick. This is, by the way, the same way you would do it in C++ if you wanted to see a value in binary. You'd do a loop and you would do shifts. I don't have time to do it today because I've run out of time, but all of these bitwise operations are available in most high-level languages. So in C++, as an example, you have you can do AND bitwise in C++. This is a bitwise OR C++. This is bitwise XOR C++. You have NOT. Those are all available. Also, by the way, depending on the arguments to this operator in C++, it will be interpreted as a shift. So you could do something like, which is the value x shifted 1 to the left. Isn't that cool? You can also like shift the value x to the right by 4 bits if you want to. Yeah. So anyway, I'm sort of closing out by just pointing out to you that your high-level languages have these same operations. You don't tend to encounter them when you're in college much, but they are there and there are applications of them, and that's one of the reasons I'm asking you to go look it up, is because there are uses for them in the real world. So if you're aware of those, then you might pull off a cool algorithm one of these days using them. Okay. I need to stop. Thanks for hanging out for the extra time. Hope everyone has a good week. We're chewing up a lot of semester these days, so I hope you're feeling good about things, at least in my class or classes, as good as you can, but I hope that all the other stuff that you're up to is going well for you also. and take a few minutes to yourself and do something that helps you relax or gives you some amount of pleasure. So I'll see you next week on Monday morning. Take care.